Hello, today's lesson is about adding and subtracting rational expressions. We're actually just getting ready to add and subtract rational expressions. We're not actually going to do the adding and subtracting yet, and it will take a couple of lessons to get to that point. First, let's just do a quick reminder. If we were going to add two fractions together, remember, if we have the same denominator, that's our common denominator, and you would just add the numerator and keep the denominator the same. So as we get into adding or subtracting rational expressions with the same denominator, we'll do the same thing. We'll keep our denominator the same. We won't add that together, just keep that denominator, but we do add the top. Now, when we don't have a common denominator, we have to find a common denominator. So we'll take the higher number, and we might count by that number, 3, 6, oh wait, 2 goes into 6, so that's our least common denominator. And since 2 times 3 is 6, then 1 times 3 is 3, or 3 times 2 is 6, so 1 times 2, 2, and now we have our 5/6 answer. And that's just old fractions that we learned a long time ago. Sometimes we get a little rusty with fractions, but we're going to apply these same concepts to rational expressions. So let's begin with that. First thing, if we have a common denominator, such as a over 6 plus 3a over 6. We'll leave the denominator the same, just as we did a moment ago with those sevenths, and we'll add the numerator. Once we add the numerator, we have to ask ourselves, just like we did at the beginning of this chapter, is it simplified? If it's not simplified, then simplify it. That's 2/3, and the a stays right where it is. Here's another example with common denominator of x plus 6. You're like, what? A denominator can be a binomial? Yes, it can. This is a common denominator. This common denominator, again, stays the same. The numerator, put it together, x squared minus 36. But now the question again is, can it be simplified? The answer is yes, because now our numerator is a difference of 2 squares, and it factors into the conjugates x plus 6 and x minus 6. So with the denominator of x plus 6, we can see that our x plus 6 binomial will cancel with that denominator as we simplify it, and our answer will be x minus 6. For our final answer, sorry, I forgot to box my answer there. So when you have a common denominator, it's just a matter of doing exactly what we did with the sevenths in the first example, and then simplifying as we did in section 8.1. All right, let's look at a couple more problems. Very similar to these. Still using the notes, and of course these notes are coming straight from the notes that I attached to this materials folder, and also it comes from the book, so if you're following along reading the book as well, you'll recognize these problems. So once again, if we have from example 1 and 2, 5m over 2n plus m over 2n. The 2n is exactly the same denominator, so common denominator, 5m plus m, 6m. The 6 and the 2 can be reduced, but not the m and the n, so 3m over n for our final answer there. For our next one, 2y over 2y minus 7. minus 7 over 2y minus 7, something slightly different happens. The denominator is a common denominator, so it stays the same. And the top 2y minus 7, so can they both cancel? Yes. But what do they cancel to? Do they cancel to 1 or they cancel to 0? They cancel to 1. You're right. All right, so let's move on. So that's a common denominator. Now, subtraction can get a little trickier, even with common denominators. So let's take a look at example 3. We have, in example 3, 3x squared plus 2x over x minus 1 minus 10x minus 5 over x minus 1. Well, when we're subtracting, we're not just subtracting the 10x, we're subtracting 10x minus 5. So imagine there's a parentheses around there. The negative has to be distributed to both terms. So 3x squared plus 2x minus 10x plus 5. So both signs changed, not just the 10x. This is over x minus 1. Clearly, this needs some simplification. Let's very quickly change or combine our like terms in the middle to 8x. And we notice that we have a trinomial here, 3x squared plus 8x, minus 8x plus 5. And it needs to be factored. We'll start with 3x and 3x. Numbers that multiply to 5 are 1 and 5. Well, let's just drop 1 here and 5 here. Well, now you can see we would be multiplying 15, and we get 15 and 1. That's not going to give us 8, so let's swap. 5 and 1. Outer gives us 3, inner gives us 5. The signs are the same, they're both negative. So bingo, we get it. This is over our denominator of x minus 1. Usually, if you try one of your factors as the denominator, that'll help you out a little bit with your factoring as well. X minus 1 cancels, and what are we left with? 3x minus 5 for our final answer. All right, now we've done plenty of subtracting with our like terms or even like binomial terms, not just monomial terms. Now we're going to take it to the next step. How do we find a least common denominator if it's not just a number? Because it was really easy with 1/2 and 2/3 to find a common denominator of 6. How are we going to find a common denominator with variables and expressions? Well, that's our next task. All right, so here we go. Let's stick with our first example, 1 over 6y, comma, 3x over 4y plus 12. Now, first thing we need to do is look at our factors. Can this be factored? No. Can this be factored? Yes. So this can be factored and changed into 3 over x, factor out the 4, y plus 3. Now we have all of our factors. So what we'd have to do, I'm going to go through the explanation, which says factor each denominator completely. We did, check. Now you want the product of all what they say unique factors. Now notice we have a digit. We have a digit 4 and a digit 6. First, we want the least common denominator for the digits. Look to the highest one, 6. Does 4 go into 6? No. So 6 times 1 doesn't work. 6 times 2 is 12. Does 4 go into that one? Yes. So 12 would be your least common denominator for the digits. So let's start with 12. Now, do we have any variables? Yes, we have a y. So we just take that y. Now, typically, if there was more than one y, and this one doesn't count because it's part of a binomial, if there was another, like a y squared or a y to the third, we would take that and we would use the highest exponent. So we'll have some examples where that happens coming up. So we only have a y to the first power, so that's what we get, y to the first power. And then any binomials that we have one binomial, y plus 3. So there we go. This is our least common denominator, 12y times y plus 3. So the LCD of our two common numbers, and then our only variable and our only binomial. And we put all those factors together. That is our least common denominator. All right, let's look at another. Probably should have started with this one, but what if we just had that good old 1 over 8, for example, and 3 over 22? Numerator doesn't really matter. How would we find that LCD? Just two numbers, like I showed you a moment ago, the LCD. We're going to start with 22, count by 22 times 1. Does 8 go into that? No. 22 times 2. Does 8 go into that? No. 22 times 3. 8 doesn't go into that. 22 times 4. Yes, 8 goes into 88. So 88 is their least common denominator. Okay, going back to an expression before we jump in to another one that has a binomial variable, a little bit of some binomials. Let's try 7. This is example 4. 7 over 5x. And 6 over 15x squared. Well, again, let's look at our digits. 5 goes into 15, so we don't have to really search very far. 15 is the numerical part of our LCD, or our coefficient. We have x in both places. We're going to take the highest. So 15x squared is one of our denominators, and it is the least common denominator. All right, as I said, let's jump to one with some binomials. All right, so we've got 4 over x squared plus 4x plus 3. 4x minus 2. And we've got x squared plus 10x plus 21. First thing we have to do is make sure that anything that can be factored, any denominator that can be factored, is factored. So let's factor this one and this one. X, 1, and 3, same sign, both positive. Factored. Done. X, what numbers multiply to 21 and add up to 10? Yep, 3 and 7. Positive means the same, both positive. All right, so this is the denominator here, and this is the denominator here. You can see they have an x plus 3 in common. So we'll get to that. What do you do if there's a common one? How many times do you use it? Well, you only use a factor one time unless it has a higher exponent. So if this was x plus 3 squared, I'd do x plus 3 squared. But I have x plus 1 here. Check. I have x plus 3. Well, I already have an x plus 3 to the first power, so I'm not going to use that one again. And then x plus 7. check. I've used every single one of the products, but I have not used them more than once. None of them had an exponential power, so I didn't raise any of them to the second power. So even though these appear twice, it only appears once because it's only to the first exponent. So that is my LCD. All right, let's try another. I got a whole bunch of these, so don't worry. We'll start with a few smaller ones and build our way up again. All right, so here is example 5. 7x over x plus 2 and 5x squared over x minus 2. Well, you might be thinking, can I factor out a negative? Can I change one of these? You cannot. So this one has a factor of x plus 2. This has a factor of x minus 2. You have to take one of each, and that is now your LCD. That's it. So nothing special there. All right, that was A. Here's B from example 5. 3 over x and 6 over x plus 4. Well, our first factor is x. Some of you might say, well, we can't take that x. We already have an x. No, but this is a different version. This is a binomial, so that one travels all together, one of each. So these were super simple because they didn't need to be factored. The denominators were already in factored form, and you just had to take one of every factor. And there were no duplicates, so no problem. All right, let's go to another. Let's bump it up again to another level. Example 6. So in example 6, we have 6m squared and 3m plus 15 and 2 over m plus 5 squared. So here we do need to factor. We can take out a 3 and we have m plus 5 left, which makes sense because now we have a common factor, m plus 5. So I've got a 3, I have m plus 5. Well, I'm not going to use it again, except for the fact that this is an exponent of 2. So now we use the highest exponent. So even though there's 1, 2, 3 m plus 5s, we only do m plus 5 squared because that's the highest exponent available. And that's our LCD. All right, next one, example 6. So that was 6. This is example 7. So we've got t minus 10 over t squared minus t minus 6 and t plus 5 over t squared plus 3t plus 2. All right, so both of these need to be factored, both denominators, before we find our LCD. Six can be 1 and 6 or 2 and 3, but they have to be different signs, hence the negative, and they have to subtract and give us negative. So let's try negative 3 and positive 2. Multiply to negative 6 and add up to negative 1. So that one's factored here. T and T, 1 and 2 are the only multiples. They're the same, both positive. So we can see we do have a common factor of t plus 2. We don't have an exponent, so it just stays t plus 2. T minus 3 is another factor, and t plus 1 is another factor. And it doesn't really matter what order you put them in. If you had started with t plus 1 and then t minus 3 and then t plus 2, you'd still be correct. There's our LCD. Now, what happens if, in example 8, they almost have matching LCDs? We have 2 over x minus 2, and we have 10 over 2 minus x. Well, some of you might think, well, these are different, so I just have x minus 2 and 2 minus x, and there we go. That's my LCD. But no, what we learned in our previous lessons is that you can take a subtraction problem, a binomial, and turn it around as long as you factor out a negative. So that's what we're going to do. We're going to factor out that negative and turn it around. So what is the LCD? Well, it's not just x minus 2. There's a negative 1 here as well. Negative 1 times x minus 2, or negative x minus 2. So we have the same binomial and the same coefficient, or the negative 1 coefficient. Should say multiple, negative 1 multiple. All right, next one up. We've only got 3 more to go, and this time, now we're going to start talking about how do we transform a number into a new fraction. Or, for example, if I said, hey, let's change a half into what over 8? Well, 2 times 4 is 8. So 1 times 4 would give us 4. And 4 over 8 would be our new fraction. So we're going to do a simpler step. Now that we know how to get the LCD, we're going to do a similar step with changing the numerator. So we're getting all of these together so that in the next lesson, we can add together those fractions that have unlike denominators. Luckily, we're not quite there yet. All right, so this is example 9. A. 4b over 9a. And we're going to transform this so it has a common denominator, I should just say. We don't have two expressions to add together yet. So let's say we're going to transform this fraction so that if this was the denominator we wanted, we would have a new numerator. So we're going to figure out what that is. Well, let's see what we've got. We have a 9. We want a 27. Well, we know that 9 times 3, I'll just use a dot, times 3 is going to give us 27. We have an a, but we want an a squared, so we need another a. We don't have a b here, but we do have a b here, so we also need a b. So we're going to multiply by 3ab to get from here to here. Well, that's what we're going to do at the top. We're going to multiply by 3ab. 4 times 3 will give us 12. There is no a, but times a will give us a, and b times b will give us b squared. So our new numerator is 12ab squared. Next. (7x) over 2x plus 5 is equal to what numerator over 6x plus 15? All right, now the first thing that we want to do is factor this, because it's really hard to see what to multiply this by to get to that. Some of you will go, that's not that hard. You multiply by 3. But if you factor it, you can see, okay, yes, it is 3. To get from here to here, all we have to do is to change it, is to multiply by 3. Multiply by 3. So what are we going to do in the numerator? Multiply by 3. 7 times 3 is 21. And x. And then we have our new numerator. So what happens when the denominator gets a lot longer? Okay, let's include some more binomials. So our next example 10, we have 5 times x squared minus 4 equals what new numerator over x minus 2, x plus 2, make that a better 2, and x minus 4. Like, wow, that's a really long denominator. Well, luckily you didn't have to factor anything out to get that denominator. This one we do have to factor the difference of 2 squares. So a difference of 2 squares factors into conjugates. Now, we have an x plus 2. We have an x minus 2, but we don't have an x minus 4. So that's what needs to be multiplied in the numerator. Well, if we say 5 times x minus 4, we've got to distribute it, right? Well, you don't have to have the distributed answer. You can just write 5 times x minus 4, and you're done. And anybody who thinks, oh, I need to cancel this, no, your answer is this numerator. It's the numerator that they're asking for, so you will only provide that numerator in your answer. Okay, and that is example 10, and that is the final for section 8.3. When we look forward to section 8.4 next, we'll start actually adding those numerators together with those unlike denominators, and we'll be doing a lot more steps. So get ready. All right, good luck with 8.3. You have 2 different homeworks on this, so this lesson provides both of those, so you get plenty of practice before we jump into the deeper end of the pool with this. Right. See you next time.